Hello, and welcome to 4.1. This is orthogonality of vectors and subspaces. I was going to break this lesson, or this section of the book, up into 3 videos and try to keep them fairly short. 1, because of my space on my phone, but 2, just to kind of help parse it up a little bit, and instead of it being one longer video, because this is a shorter section. It's only roughly about 3 or 4 pages, especially with what we're going to focus on. And so this is a really important lesson because it's what reminds us and introduces us to the concept again of orthogonality. And if you remember, 2 vectors v and w are said to be orthogonal if v transpose w, in other words, the dot product of these 2 vectors is equal to 0. Orthogonal implies that 2 vectors are perpendicular, but what we're going to do is expand that into subspaces where we start to now talk about subspaces being perpendicular. So say, for example, if I have a line which is in 1 dimension in a 2-dimensional plane, these 2 spaces, subspaces, can be orthogonal as long as this line is perpendicular to every vector in this plane. For example, this board is a 2-dimensional plane, and by putting my marker dead center on it coming out towards the camera, no matter where I place my marker, it is always at a 90-degree angle. And so spaces themselves, every vector that I could mark here with my marker, and every vector inside the plane would said to be orthogonal. And so we start to think about how this extends, and then ultimately how this connects to the 4 fundamental subspaces that we learned about at the end of Unit 3. I have kind of been diving into for this entire piece. Textbook. And so if we want to think about this, specifically the 4 fundamental subspaces, we actually kind of pair them off. And so what's really, really interesting is that a vector in the null space for a matrix A, so let's just say a vector in the null space of A is orthogonal to every vector in the row space of A. And so if I'm looking at, and I could say every vector in the null space of A, when I look at this in terms of spaces and then bases for these spaces, what we're essentially arguing is that these bases, these spaces, subspaces themselves are orthogonal, that they're at 90 degrees. And that if I essentially take a dot product of a vector in the null space and a vector in the row space, we're going to get 0 as the inner product. And there's 2 proofs for this. And the way that I kind of looks at it, I think the first one is the only one that I'm going to kind of focus on, is it starts with looking at just AX is equal to 0. If we're looking at this system, if X is a solution to this, then X is in the null space of A. And if I think about how this multiplication essentially works, I'm taking every row of A, so think row 1 of A, row 2 of A, and if this continues all the way down to row M of A, I'm essentially dotting this with the vector X, X1, X2, all the way down to Xn. And essentially creating a bunch of zeros. Like this is essentially saying row 1 dotted with X. This is row 2 dotted with X, all the way down to row M dotted with X. And each of these products would be 0 all the way down because of this initial setup. And so remember that if X came in the null space, then by dotting it with each row, and therefore every row being in the row space of A, even if these are combinations, like not every, maybe the dimension of the row space is an M, for example. Maybe some of these are dependent, but then that means they're combinations. Their products are still going to be 0 when I'm going through and dot producting these things together. And so what it's kind of showing you is that each row dotted with something in the null space is 0. They're orthogonal by the definition that we had up earlier. It's just a really clean look and setup, and there's a little bit more of a formal idea that he gives. It's equation number 2 in the textbook. But I think this gives a good visualization of kind of what's happening and something that we'll use in the first example to kind of show. But essentially what that means then is that the null space of A is orthogonal to the row space of A. If that's true for every vector in these spaces, then it's true amongst the subspaces themselves. And I have this pair. Well, we also have the other pair, which is the column space of A is orthogonal to the left null space of A. So if I was to take a vector in the column space and dot it with the vector in the left null space, that dot product would always be 0 as well. We'll talk about that a little bit more. I'm going to show you an example here so you can kind of see some numbers. And it's an example taken from the textbook, but I'm going to add a little bit more work to it so you can kind of see and make the connection with what we've done in Unit 2 and Unit 3. And in particular, the last lesson of Unit 3. And I'm just kind of looking at the textbook. And then what that'll kind of lead into is a conversation around dimensions. If I look at the dimensions of the null space and the dimensions of the row space, if I add those two things together, it'll give me the overall dimension for Rn versus if I take the column space and the left null space of A, if I add those together, that'll keep me in Rm for rectangular matrices. And then in the final video, we'll start looking at, well, if these are square matrices, then the bases themselves that form these spaces essentially cover the entirety of the space. And we can essentially separate any unique solution to a system into a vector that's in the row space and a vector that's in the null space, focusing on just those two right there. And so that's what we'll get in terms of the third video. And so let's take a look at the example now and just kind of showcase this with numbers and with a specific matrix. And so I'm going to go through and find each of these subspaces, the row space, null space, column space, etc., with the purpose, again, of showing you how they're orthogonal. And so let's look at, this is the example 1 taken from the textbook with my matrix A, 1, -2, 1, 1, 0, -1. Initially, when I did this earlier, I was working this problem and wrote this down wrong, so be careful. If I want to find the row space, remember the row space focuses on finding the column space of A transpose. The whole purpose is to transpose it. And that, in fact, is actually the proof of showing that these, looking at the column space and the left null space is also orthogonal, very similar to what we did with row space. I just make the argument for the transpose. Let's look at this transpose matrix. So 1, -2, 1, 1, 0, -1. And what I'm going to do is take this down into reduced row echelon form. And again, what I'm checking for literally, is really just kind of showcasing that these two rows are linearly independent. That these two rows form the row space for this matrix. Because when I go through and perform my elimination, times 2 and add, so first row is going to stay the same. Times 2 and add means that's going to zero out. That's going to give me 2 here. If I do this row minus this row, that's going to 0. -1 minus 1 is -2. And notice I can replace this row by just adding these two. That's going to zero this row out. And so notice I've got 2 pivots. And because that comes from the 2 rows, these 2 rows are linearly independent. I can divide this by 2 and then cancel this entry out, and we have the identity matrix. And again, what that's showcasing is that these 2 rows are linearly independent. If I wanted to think about the basis for my row space, it's formed by the 2 rows, 1, -2, 1, and 1, 0, -1. Notice how those are the transpose of those. And so that forms the row space. Well, if I want to look at the null space for this matrix, so I'm going to go through and let's find the null space. I want to leave the matrix as is and produce, or essentially transform this into reduced row echelon form, reduced row echelon form, tongue twister. Again, taking this row, subtracting row 1 from it. Row 1 staying the same. 1 minus 1 is 0. 0 minus -2 is 2. -1 minus 1 being -2. Notice a similar kind of format. And then notice I can eliminate this entry here by adding those two. I feel like I did something wrong. Sorry, not eliminating, sorry. I've got a pivot here. I was thinking of something. I've got a pivot here. Notice how I've got a free variable column. And so this is telling us that the null space has a dimension of 1. And so what I'm going to do is not eliminate this entry, but eliminate this entry. It's where I was kind of getting backwards. And so I want to replace row 1 by adding row 2 to it. And so that's going to add to zero this out. And then add, but this might throw us off. I think what I ended up doing was simplifying a little bit more. -1, so that's actually okay. It's a -1 here. And then if I divide this by 2, 1 and -1, here are my independent columns, so here and here, which makes sense. My third column is a combination of these two. It has to be, like we've talked about in Unit 3. And this identifies the special solution. We were using S, there's only one here. But being the third column, this kind of tells you that this is 1, 1, and 1, taking the opposite of these. Again, you can multiply this here and see, okay, well 1 minus 2 plus 1 is 0. 1 plus 0 plus -1 is also 0. And notice how just checking that, like what we saw in the proof, is I'm taking a vector that's in the null space, this just being the core, because really any scalar of this would work, and I'm dotting it with each row of A. Well, that's the vectors that are forming the basis. And that creates 0. In other words, the dot product of something in the null space and the dot product of something in the row space is 0. They're orthogonal to everything when I go through and multiply this out. And so that shows orthogonality. We have that dot product, and we see that kind of written out, that AX is equal to 0. And then the other thing I wanted to kind of showcase is if we were to do this in terms of the column space and we looked at the left null space, we would get a similar result. If we look at our work here, the column space is the basis formed by the first two vectors. That would be the independent. So my column space, I'll put that here. So C of A. The basis would consist of the vectors 1, 1 and -2, 0. If we look at the null space for A transpose, so the left null space, we've already got the transpose here. Notice how that would be the 0 vector. This is completely covered, so there's no free parameter, free variable. So the null space actually only contains the 0 vector. 0, 0, essentially, since we're in Rn. And so the null space would contain that. And then very clearly, like if I dot product these, like, I'm always going to get 0. And again, it makes sense because if you look at the column space of A, this covers all of R2 because we're in two-dimensional space and I have two vectors. So the only thing that's orthogonal to that would have to be the 0 vector. This kind of creates everything. So there's no other two-dimensional there. That would get us 0. And this is where like the observation, I think, is kind of important because this will what leads into part 2 of the videos. Is especially like right here, like notice how the column space has dimension of 2. The left null space specifically has a dimension of 0. And so if I add these two things together, we get 2. Well, this was equal to m. This was our number of rows. And if you remember, the column space and the left null space are subspaces of Rm. So in this case of R2. And again, we're seeing that the column space covers all of it, so the left null space is 0. Now, if we look back at the row space, notice the row space had a dimension of 2. I had 2 linearly independent rows. The null space has a dimension of 1. And if I add these two dimensions together, we get 3, which is equal to n. I had 3 columns to start in terms of this matrix. And so there looks like to be some kind of connection between the dimensions of these subspaces that are orthogonal to one another and the overall number of columns and rows that we see in our original matrix. And that actually lends itself into fundamental theorem of linear algebra part 2. And that's what the second video will dive a little bit deeper into. So here's an example kind of outlining again how the subspaces are orthogonal and kind of seeing it with some numbers. But hopefully the proof at the beginning kind of makes sense without diving too much into specifically these two in terms of proving.